Hello, am I audible?
Am I audible? Am I audible? Am I audible? Clearly. Okay. Okay. Hearty welcome to the webinar on next generation challenges in astrotechnology, organized by the Department of Basic Sciences and Humanities, Rajagiri School of Engineering and Technology. We have 5
So sorry for the interruption. Hearty welcome to the webinar on next generation challenges in Astrotechnology, organized by the Department of Basic Sciences and Humanities, Rajagiri School of Engineering and Technology. We have 510 number of participants. Am I audible? Sorry, there are some technical errors. Okay, I'm starting. Hearty welcome to the webinar on next generation challenges in Astrotechnology, organized by the Department of Basic Sciences and Humanities, Rajagiri School of Engineering and Technology. We have 510 number of participants registered for this webinar. Our speaker for the session is an eminent personality, Professor A.N. Prakash from Inter-University Center for Astronomy and Astrophysics, Ayuka, Pune. Professor A.N. Prakash is an engineer by profession, and he is also a scientist. He works in the interface between astronomy and engineering. Recently, there has been an increased demand for engineers in astronomy because of the sophisticated instruments which have to be built for astronomy instrumentation engineer. And his lab at Ayuka is providing instruments to many telescopes all over the world. He is the apt person for talking about the interface between astronomy and engineering. I hope this webinar will be very beneficial to young engineers and also to the student community. Now, there are some instructions to the participants. All of you should mute your mic and turn off your camera while the program is in progress. If you have any question, please type it in the chat box. And the questions will be answered at the end of the session. Please do ask questions connected with the talk as far as possible. Now I hand over to the head of the Department of Basic Sciences and Humanities, Dr. Sonia Paul, to welcome and introduce the speaker.
Thank you, Dr. Rinku Jacob. Good morning to one and all present for this session. On behalf of Rajagiri School of Engineering and Technology, I welcome all of you to this national webinar on next generation challenges in astrotechnology. It is my privilege to introduce our speaker for the session, Professor A.N. Prakash, Head of Instrumentation at Inter-University Center for Astronomy and Astrophysics, Pune. Dr. Ram Prakash did his BTech in electronics and then went on to do his master's and PhD in physics. He has been a visiting fellow specializing in the area of astronomy at the California Institute of Technology, USA, and has also been a postdoc fellow in the discipline of instrumentation at the Institute of Astronomy, Cambridge, UK. He joined Ayuka in 2000. Dr. Ram Prakash also holds academic positions at the Indian Institute of Astrophysics, Bangalore, Center of Excellence in Space Sciences at Indian Institute of Science Education and Research, Kolkata, and California Institute of Technology, USA. Besides being a research fellow at the Institute of Astrophysics, Foundation for Research and Technology, Crete, Greece. He has contributed in various capacities to many projects at the national and international levels. I will list some of these for the audience's benefit. He is the principal investigator of the project, Devasthal Optical Telescope Integral Field Spectrograph, and is the instrument principal investigator of the Solar Ultraviolet Imaging Telescope on board Aditya L1 mission, the first dedicated solar mission of ISRO. He is the associate program director of the India TMT 30-meter telescope project, funded by Department of Science and Technology and Department of Atomic Energy. He was the co-principal investigator of the collaborative project RoboPol, which is a specialized photopolarimeter designed specifically for a 1.3 meter telescope at the Skinnekes Observatory commissioned in 2013. He was the co-principal investigator of the collaborative project Wide Area Linear Optical Polarimeter, as well as RoboAO, which is the first autonomous laser adaptive optics for few meter class telescopes. It goes without saying that Dr. Ram Prakash has published widely and has more than 100 publications to date. He is also a thesis advisor and postdoctoral advisor. He has supervised over 25 undergraduate and over 15 postgraduate student projects. Many of these students have subsequently been attracted to and successfully taken up mainstream research in physics, astrophysics, and engineering. Dear participants, I'm sure all of you would agree that it is indeed our good fortune to have with us such an accomplished academician and researcher who will provide us with a fascinating and informative insight into the realm of astrotechnology through this webinar. I welcome you, sir, to deliver the webinar.
Good morning, everybody. Thank you. Sorry. Thank you, Dr. Rinku Jacob and Dr. Sonia Paul for the kind introduction. I will straight away start with the topic of today's presentation, which is next generation challenges in astrotechnology. I will, for the moment, keep my video off and maybe restart it when the question answer session starts, just to conserve bandwidth. I have some movies in my presentation, so the video may create problems when both movies and the video are on. So bear with me when I have my video off for the moment. As Dr. Rinku Jacob mentioned in the beginning, astronomy is passing through a very important phase right now, which is going to be really a game changer in this area over the next decade or so. This is not the first time this has happened. This has happened in the past. When Galileo first used his telescope to look at the sky, a new world opened up to humankind, and we started seeing things which we were never seeing before. We started understanding things which in a way we never realized before. And such things keep happening. So a few hundred years later, when the 1 meter class telescopes became operational, we started seeing a very new world. For example, it was using 1 meter class telescopes several tens of years ago that we discovered that our universe is expanding. The whole concept of the entire universe being possible to expand and space itself expanding is an extremely non-intuitive realization. So as generations of telescopes got built from Galileo's times, or even before, you could say tools which are not really telescopes, but tools used for astronomy. From then onwards, as these tools and their techniques and technologies kept on improving, our worldview has substantially changed. I will come to this topic toward the end of my presentation, but that is what the core message of this is. So let me, before getting into modern astronomy technology, let me start with things which which has existed in the past. It's just one or two slides. This is the image of Stonehenge in southern England. Just an array of large stones in ruins. And it was supposed to be built in 2000 BC. Now, the amazing thing is the structure of the stones and the alignment seem to have a close correlation with celestial events, like the summer solstice, winter solstice, and so on and so forth. And even more amazing is some of these stones are 50 tons heavy. And the kind of rock from which these stones have been cut out is nowhere seen in southern England. The nearest place from which these kind of stones could be quarried are 100 miles away at least. So in 2000 BC, human beings took effort to quarry stones which are certain properties and transport them 100 miles and identify a place where the structure can be set up and this is astronomical significance. This is just an artist's impression of what the Stonehenge would have looked like when in its heyday. Now, this is just not a unique example. There are many examples. For example, here is what is called a sun dagger. The interesting thing is you see this spherical pattern carved out of rock here, and sunlight creating a dagger-shaped shadow on those spiral structure. And as seasons change, this dagger's position on the spiral structure keeps moving. And that's a mark of the change of seasons. Now, the amazing thing is that structure, the spiral pattern and the sunlight shadowing arrangement has been created on top of this, this outcrop in the middle of a desert. So in those days, hundreds of years ago, people made such a tremendous effort to climb on top of this mountain or this hill, create these structures, and so on and so forth. So similarly, for example, there is the pyramids of Egypt. The people believe that the structures within the pyramids of Egypt has alignments with respect to celestial objects in the sky. So it may be true, may not be true, but it is believable because the celestial phenomena are where the most and continues to be the most impressive phenomena that happens around us. The kind of excitement that is created when a solar eclipse happens or a similar event happens on the sun is unheard of. It's the most mesmerizing among the natural phenomena we can think of. So it naturally would have attracted attention of people of those ages, and they would have made a tremendous effort in those days to understand those things. And the story continues. The story continues till date. I will try to build that picture as we move forward. But as I said earlier in the beginning, telescopes are the tools which revolutionized our understanding of the skies and the objects we see in the skies, like the stars, the galaxies, and other distant objects. Now the question is, how does the telescope help an astronomer to do this? What essentially does a telescope do? If you just break that question into a simple English answer, you say, if you look through a telescope, objects appear closer. Now, there are two aspects of bringing objects closer. When an object appears closer, you start collecting more light. And when an object appears closer, you also start seeing more details of that object. And so the object becomes brighter and you are able to see finer details. And both of these aspects are very important for astronomy. To study very faint objects, which are otherwise invisible to naked eye, and also to study them in great fine detail so that the fine structures are understood. Both of them are very important in modern astronomy. Now, it's a telescope's diameter which defines how much brighter an object becomes. The larger the diameter of the telescope, the more light it collects, and the brighter the object appears. And similarly, it's the focal length of the telescope which defines how fine details it can see. So as a comparison, if you take Galileo's telescope, it has a diameter of about 40 millimeters. But the most advanced modern telescope, the Keck telescope, has a diameter of about 10 meters. Similarly, Galileo's telescope had a focal length of about 400 millimeters. The Keck telescope has a focal length of about 150 meters. So we have come a long way from Galilean times into modern times in both these abilities of the telescope. How large a telescope we can build, and which means how faint objects you can see, and how fine details you can see. Now the question is, how exactly does this happen? If there is a point source in the sky, how does a telescope collect more light from a point on the sky? So let me illustrate that by this slide. I put a star, before going to that, let me at least bring to your attention what are the distances involved in astronomy. When you say telescope bring objects closer, how far away are astronomical distances? So one of the units which astronomers use to measure distances in astronomy is an astronomical unit, very obvious name. It is the mean diameter of the Earth's orbit around the sun. So we know that sunlight takes about 8 minutes to travel from sun to Earth. So 8 into 60 seconds times the velocity of light, which is 3 into 10 raised to 8 meters. So this translates to about 1.5 into 10 to the 11 meters. That is the mean sun-Earth distance as Earth goes around the sun. Now, this unit itself is not very large for astronomy purposes. So we have designed another unit called the light year, which all of you are familiar with, distance traveled by light in 1 year. So if the number of seconds in a year is about 3 into 10 to the 7 times the velocity of light, so 10 to the 16 meters is roughly 1 light year, which is considerably larger than 1 astronomical unit. Now, if I take even this light year distance may not be large enough for astronomers, so we define a larger distance unit. To define that unit, what you do is to do the following. You take a stick like this, and if you draw 2 lines from the edges of the stick, which in a way that they converge to a point, as you move the stick further and farther away, the angle subtended by these 2 lines from the edges of the stick will become smaller and smaller. So the stick is farther and farther away from you. You are sitting here and looking at the stick. As the stick goes further and farther away, this angle becomes smaller and smaller. Now, if I take a stick which is 1 astronomical unit in size, this size, and define how far away do I have to go so that this angle subtended is just 1 arc second. Now, 1 degree can be divided into 60 arc minutes. 1 arc minute can be divided into 60 arc seconds. So just like time is divided, 1 hour into minutes and minutes into seconds, degree into arc minutes and arc minutes into arc seconds. So arc second is a very, very tiny angle. So if you have to get 1 arc second angle between these 2 lines for a stick which is this large, 1 astronomical unit large, this distance has to be very, very large, and that distance is called 1 parsec. You can pretty easily show that 1 parsec from basic geometry, that 1 parsec is about 3¼ times a light year. So this is typically, parsec is typically a unit which astronomers use to measure distances. Now, if I take the nearest star to our solar system, it is called Proxima Centauri. distance to that, so that star is about 4.2 light years or about 1.3 parsecs. The size of our galaxy itself, the Milky Way galaxy, is 20,000 times that, 20,000 parsecs. So if the nearest star to the sun is about a parsec away, our galaxy is 20,000 times larger than that. The distance to the nearest small galaxies, called the Magellanic Clouds, to our galaxy is about 50,000 times, 50,000 parsecs. If you take the distance to the nearest galaxy, which is called Andromeda, it's almost a megaparsec, another factor of 1,000 larger. So interstellar distances are typically parsecs. Intergalactic distances are megaparsecs, and galactic sizes are of the order of kiloparsecs. Now, if I take the size of the visible universe today, it is another factor of 1,000, like 4 gigaparsecs. So you can see that these distances are amazingly, astonishingly large. Even the Earth-Sun distance is very, very large. Light takes at its speed of 3 lakh kilometers a second. It takes 8 minutes to reach us. And compared to that, these distances are several factors of 1,000 at each scale, from interstellar distances to the size of the galaxy, to the intergalactic distances, to the size of the visible universe. So enormous distances. So in this context, what does it mean by telescope bringing an object closer? An object like a star at this enormous distance away will look like a point in the sky. So what does it mean by a big telescope will collect more light from that star? To illustrate that, I just I make this slide. Here is a star which is radiating light away in all directions. So the light is emitted by the star and is radiating away in a spherical fashion. So at a given time, all the light started from the star would have reached a specific distance away from the star in a spherical shape. So that shape is called a wave front, because that is as far as the light wave would have reached in a given time. Now, if you think of that light which is traveling parsecs and kiloparsecs and megaparsecs and even gigaparsecs of distances, so the diameter or the radius of the sphere is infinite. So what happens is, if you are sitting here on Earth and looking at that star, all the rays which radiated away from the star radially in a radial direction will appear to arrive at you parallelly, because the sphere of the wavefront has expanded so much that it has almost become a plane surface. A sphere of infinite radius is a plane. So the wavefront which is arriving at your telescope, however large it is, because this distance is infinite, practically, the rays appear parallel, or the wavefront appears like a plane wavefront. Now, if I take a telescope here, and telescope is this big, I hope you can see my cursor. If the telescope is this big, you will collect that much light from that star. The telescope is this big, you will collect that much light from the star. So depending on what is the diameter of your telescope, it's collecting aperture of the telescope, you collect more light from the same star, and that star appears brighter to you. Instead of a telescope, if you put your eye here, in dark conditions, your pupil is open to about 8 millimeters. So your eye is like a telescope which collects light over an 8 millimeter area from this wavefront. On that other hand, if you put a 10-meter diameter telescope, it is collecting over an area of 10-meter diameter from the same star, and the star appears brighter. It's collecting more light. Now, how does the telescope allow you to see fine details? In order to see that, I put a second star right next to the first one. Now, if the telescope is able to see the light coming from the red star differently from the light coming from the black star, then they will appear as two stars. Otherwise, it will appear to be one blob of light to you. Now, how does the telescope distinguish the light coming from the red star? Now, if you think of the light radiating from the red star, it will arrive here as a plane wavefront, with the rays are all parallel, mostly parallel. But they will arrive at an angle because this wavefront is now centered on this star, red star. The red wavefront is centered on the red star and the black wavefront on the black star. And because of that, there will be an angle of arrival difference. So if the telescope is able to measure this angle of arrival difference, it will see these two stars as two stars. If the telescope is not able to measure this angle of arrival difference, it will see these two stars as one blob of light, and you will not be able to distinguish the details. So the ability of the telescope to see the angle difference is defined by the focal length of the telescope. And that's what I would illustrate here in a 10 standard ray diagram. I'm representing the telescope with a lens here, a symbol lens. So if an object is sitting directly on the axial direction of the telescope, infinitely far away, light from that object will appear parallel to the axis of the lens, and they will focus at the focal plane of the lens, which is the telescope. And bigger the diameter of the lens, the more light it collects. Now, if I put another star, which is a red star, light from that star will arrive on the telescope at an angle. And we know from 10 standard ray optics where that light will go to the focal plane, which is here, because the light passing through the center of the lens pass undeviated. So all the red rays from the red star would arrive here. So what the telescope is doing is it's converting angular separation in the sky to linear separation in its focal plane. A given angular separation of two objects in the sky, two stars, is translated to a linear separation at the focal plane of the telescope. Now you can do some basic arithmetic geometry, where you say if this angular separation in the sky, this angle, which is the same as this angle, is theta, and if the focal length of the telescope is f, this linear separation is nothing but h is equal to f theta. So if h is equal to f theta, then you can translate that and then define something called a plate scale of the telescope, which is the angle on the sky which correspond to 1 millimeter separation of the images at the telescope's focal plane. That is called the plate scale. And this expression is, you can easily demonstrate that it is 206.265 by f arc seconds per millimeter, where this number in the numerator is nothing but the number of arc seconds in 1 radian. Because this expression is in radians, to translate that into arc seconds, you need to multiply by this factor. Otherwise, it is just 1 by f radians per millimeter. So you can clearly see that it's the focal plane of the focal length of the telescope, which defines what the separation in its focal plane is, and thereby what fine details the telescope is able to show. So clearly, the astronomer's quest is to make telescopes which are larger in diameter and larger in focal length. Now, if you make telescopes bigger and bigger, how faint can you see? What is the faintest object you can see in the sky? That's a natural question you can ask. Sorry. So if I go out today in daytime and look at the sky, we don't see any stars. So is the faintest object you can see, can you see any object fainter than the sky itself? The sky has some light. Even if you go out in the night sky also has certain brightness. It is not zero, it's not emitting zero light, it's still emitting some light in even a night sky. So if a star is fainter than the night sky brightness, can you see it? So I am illustrating that in a figure here. It is this, think of this as a patch of the sky on which there is a very bright star. Of course, if it's a bright star, brighter than the sky, you can see it. Now, PowerPoint allows you to make this star fainter and fainter. So I'm going to do that. I've made the star slightly fainter again. You still see it, but if it becomes even further fainter than the light emitted from this patch of the sky, you are not seeing it. I've not removed the star. The star is still there. I've just made it fainter. To convince you that that is the situation, let me make the sky a little fainter, and the star should reappear. See, when the sky is darker, the star has reappeared. It's still there. You just don't see it because the sky is brighter than that. So does it say that, does it mean that if an object is fainter than the sky, you cannot see it? If that is the case, there's no point in making a telescope bigger and bigger, making bigger and bigger telescopes, because the sky sets the limit of how faint you can see. Now, what about measuring the whole light coming from this direction of the sky? Measure the light coming from this direction of the sky and subtract this sky brightness from this side. So if there is a star here, there will be an excess light from this direction, and the difference would tell you that there is a star there. I measure the light from this direction. I measure the light from this direction, this direction, this direction accurately, and subtract that light from the light from this direction. So you can see the star. Now, this is a plausible way forward, and astronomers do this, but there is a limitation. There is a limitation because any measurement you make is subject to certain uncertainty, certain error. Now, if you are making photon measurements, measurement of light, how much light comes from a region of the sky, if you make photon measurements, there is an uncertainty in measuring the number of photons you collect. This is the natural behavior of photons. This is nothing to do with the telescope. There's nothing to do with technological limitation. It is just coming out from the fact that photon emission is a statistical process, or counting of photons is a statistical process. And it turns out, if you do the mathematics properly, that if you collect n photons from any object, there is an inherent uncertainty of root n. So if you collect n photons from an object, you know that number n to an uncertainty of n plus minus root n. Because the next time you measure light from the same object, you will get a different number n. It's not the one you got the first time, because it's not exactly the same number of photons the source emitted in the next instant. And if you do that many times and measure what is the spread in the number of photons in each of those experiments, you will find that the standard deviation goes like root n. So this is a limitation. Now, if I measure the light toward this direction, I know that number only to an uncertainty of root n. Similarly, the measurement in this direction is only known to me only to an uncertainty of root n. Now, if the star light itself is not more than this uncertainty of measurement, you would not be able to conclude that there is a star there, because the star extra photons emitted by the star is less than your measurement uncertainty. Then how do you conclude that there is a star there? So that is the problem. Now let me try to illustrate this problem with a table here. The first column is the number of photons you collect from the star. Then n sky is the number of photons you collect from the sky. Sigma star is nothing but root n star. So this by this formula, the error in measurement of photons from the star. Sigma sky is the error in measurement of photons from the sky. And the total signal to noise ratio is the number of photons from the star divided by the total error. And the total error adds in quadrature. Square them and add and square root. I cannot explain why that is to be done. But take this, that the total error is the sum of the squares of the errors from measuring the starlight and the skylight and the square root of it. So this is the signal. This is the total error or uncertainty in measurement. So if the number of photons from the star is larger than this number, you can conclude that there's a star there. The number of photons here is smaller than this number, you do not know whether there is a star there or not, because your uncertainty dominates, your error in measurement dominates. So think of a situation where I'm measuring light, looking at a star which produces 1 photon across your telescope's aperture per unit time. And suppose that the sky itself is producing 100 times more photons over the same telescope aperture over the same exposure time. So the error in this is 1, error in this is 10. So if you take the sum of the squares and take the square root, this is roughly 10. So the signal to noise ratio is 1/10. If you substitute in this number, it's roughly 1/10. So the number of photons coming extra from the star is 10 times less than the total uncertainty in your light measurement. So you cannot conclude whether there is a star there or not. There is, maybe it's all because all the fluctuations is because of your measurement error. Now think of increasing the light collection either by increasing the exposure time 100 times or making a telescope which is 100 times more collecting area or 10 times more diameter. So the starlight goes up by 100, factor of 100. The skylight also goes up by a factor of 100. But now the total noise is 10 squared plus 100 squared square root, which is something like 100. But the signal is also 100. So the signal to noise ratio has now become 1, which means the number of photons coming from the star is comparable to your uncertainty in measurement. You may start suspecting that there is a star sitting there. Make the telescope larger, 100 times larger, or collect 100 times more photons from both star and sky. Now the uncertainty in measuring the starlight is 100. Uncertainty, you are going to get 1,000,000 photons from the sky, which is an uncertainty of square root of million, which is 1,000. Now the ratio of 10,000 over 1,000 is 10. So by collecting more light, what you have managed to do is to make your signal, which is the light from the star, stand out from your uncertainty in measurement so that you definitely know that here is a star. Because your uncertainty is measurement is only 1,000, while the light, extra light from the star is 10,000. And you definitely know here is a star. So that is the game astronomers play. By making bigger and bigger telescopes, they collect more and more photons and such that the fractional uncertainty, which goes only as the square root of the total photons collected, is smaller and smaller compared to your signal. And thereby you can see any amount of faint object. The larger your telescope is, the more photons you collect, the fainter you keep seeing. And the sky itself does not set a limit on how faint you can see. So that is basically what astronomers do. They make bigger telescopes, collect more photons, and keep seeing fainter and fainter objects, which they have not been able to see so far. So new phenomena start unrevealing. So here is an example of very large telescopes. This is the Mauna Kea volcano, extinct volcano in Hawaii. Its height is about half the height of Mount Everest. It's about 4,200 meters above sea level. Some of the largest existing telescopes are on top of this mountain. These are 10-meter diameter Keck telescope, which I mentioned in the beginning. There's an 8-meter Subaru telescope. So this is the 8-meter Subaru telescope. This is the 8-meter Gemini telescope. There's a 4-meter CFST, and so on and so forth. So many large telescopes exist at this observatory site. The advantage of this observatory site is it's about 4,200 meters above sea level. So most of the clouds are below this mountain. So if you drive up to the mountain top, you are by and large above the clouds and you get clear skies to observe the celestial phenomena. And so this is just a close-up view of the Keck telescope. You can see the Keck primary mirror of the telescope. These are 8 meters in diameter, 2 of them. These are huge structures. For example, this height here is about 2 or 3 stories. So if you think of this as 2 or 3 stories height, you can imagine how high this entire building is. And imagine making such a big structure on top of a mountain, which is half the height of Mount Everest, and sitting in the middle of Pacific Ocean on an island. So it is very similar to the story I first said about the Stonehenge, where human beings made enormous efforts to build structures which allow them to study the celestial phenomena. And the story continues. So Keck telescope is among the largest existing optical astronomical telescopes. And they are just an illustration of how much effort we put in to build these facilities, operate these facilities, and study the celestial phenomena. This is another marvel. It's a 5-meter diameter telescope. The telescope primary mirror is here, a 5-meter diameter telescope in Mount Palomar in California. This is the William Herschel telescope again in Spain. And this is a very large telescope, each of them 8 meters in diameter, 4 of them sitting on a very high mountain in the Andes mountain ranges in Chile. And you can see the clouds. The clouds are again below the height, the top of the summit of the mountain. And these are among the largest facilities existing in the world currently. But in the beginning, I said that astronomy is on the verge of a giant leap forward. The reason I said that is the world over, now astronomers are planning to build the next generation facilities. So as I told you, the largest existing telescope had a diameter of 10 meters or 8 meters, roughly 8 to 10 meters. Here is a 25-meter diameter telescope, which are made of 7 8-meter diameter mirrors. So each of these mirrors are 8 meters in diameter, and they're put together to form a single telescope, which is about 25 meters in diameter. Similarly, there is another effort to make a 30-meter diameter telescope. The segments here look hexagonal so that they can be packed close by, unlike the previous version. And this about 500 of these segments joined together, about 1.5 meters in size each segment. 500 of them joined together to make a 30-meter diameter aperture. And India is part of this, this effort. I will come to that a little later. This is an illustration of a 39-meter telescope, again going to come up in Chile, made of segments, but you can't see the individual segments except at the edges, which looks jagged. Each of the segments are again 1.4 meters in diameter, and about 1,000 of them put together to form a 39-meter diameter telescope. It's called the European Extremely Large Telescope. Now, these big facilities, these are not laboratory experiments. They sit on top of big mountains in very extreme conditions, and they are not also static devices. They have to track the movement of objects in the sky. For example, if you look at the sky and take a long exposure, pointing the camera towards the North Pole, this center part is the North Pole, the place where the axis of the Earth appears to hit the sky, axis of the Earth around which it rotates, that axis hits the sky at this point. So all stars in the sky appear to rotate around that axis because we are sitting on the Earth and rotating about that axis. So the sky appears to rotate around that axis to us in the reverse direction. So the stellar trails look circular about that point in the sky. Now, the rate at which a sky moves is about 24 hours. It moves about 360 degrees. One rotation in 24 hours is what Earth does, which means that in every second, the sky is moving 15 arc seconds. So here is a little time-lapse movie of star trails. So if I point towards the North Pole and take a time-lapse movie, each star will form a trail in a circular fashion, which is centered at the pole. And this star, this bright star, very close to the center is the the pole star at the north, near the North Pole. Not exactly at the North Pole, but pretty close to the North Celestial Pole. So a telescope which you build does not have to just sit as a static object on the top of the mountain. It has to move. It has to move to track the motion of these objects in the sky, because you remember you have to collect a lot of light. So even with an 8-meter telescope or a 10-meter telescope, if you look at the very faint objects in the sky, they hardly produce any photons in a minute, in a second, in several minutes. They may produce really few number of photons. Now, if you have to collect thousands of photons from that object, you have to stare at that object for a long time. So the telescope has to track the object's motion across the sky to make sure that the object is in the field of view, and you can keep collecting photons. So these massive objects these are massive structures. As shown here, this is a Gemini telescope. This glass here is 8 meters in diameter, and this entire structure, about 20 tons, have to move very precisely, sitting up there on top of the mountain in multiple axes, multiple orientations, to make sure that you can track objects in the sky. And this is not a laboratory system. This tracking has to be done in the presence of all kinds of disturbances, because when the tube looks vertically up versus the tube is looking sideways, the gravity effect is very different. The temperature of the one end of the tube and one end of the mirror can be very different from the other ends. There could be winds blowing on top of these very high mountains. All these disturbances would create havoc in how accurately you can track the motion of objects in the sky. And this has to be tackled by engineering marvels. So the whole idea of building these facilities on top of these mountains and making them behave in the precise manner which astronomers need them to behave in order to collect light from the celestial targets and see fine structures on galaxies, etc., is an amazing engineering marvel. Now, having said that, let me bring to your attention one of the most difficult limitations of astronomy today, at least optical astronomy. I shouldn't say radio astronomy, but optical astronomy. This is called seeing. The effect, I will try to explain that effect in a minute. So as light travels from this infinitely far away sources, it is passing through by and large empty space. But when it hits the Earth's atmosphere, Earth's atmosphere has about 10 to the 19 particles in every cubic centimeter. So if we take a box in the atmosphere, which is 1 centimeter by 1 centimeter by 1 centimeter in size, there are about 10 to the 19 particles in there. Even the best vacuum human beings can create on Earth by best technology will have several millions of particles in 1 cc, 1 centimeter cubed. So, but the space is by and large empty. There's not much material per unit volume in space. That is why it's called space. It's by and large empty. So when light hits the Earth's atmosphere, the atmosphere itself is not a very homogeneous static medium. It is continuously changing because of various factors like the ground heating, solar heating, wind. All kinds of disturbances cause the atmosphere to change continuously, and its density, temperature, pressure, etc., are instantaneously changing from point to point. It's not the same density, pressure, temperature, etc. at every point in the atmosphere. It's instantaneously changing by small amounts, but this matters because as light passes through this atmosphere, it gets really disturbed. Now, the main problem is it's not just that the atmosphere changes. There is structure in the atmosphere at all scales. There is a structure introduced by the overall heating of the atmosphere by sun or the ground radiation, etc., and the wind and large patterns. But the atmosphere, those blobs of moving mass breaks down into smaller and smaller pieces. So the atmosphere has eddy currents and motions at all scales, starting from a few millimeters all the way up to several tens of kilometers in size. The entire range of motion structures exist in the atmosphere. It's a very turbulent medium. Now, what happens is, I illustrate what the problem is when you look at the sky through a turbulent medium like this. Now, in this case, we have a mountain here, and wind is flowing from this direction above a calm sea. So it's very stable laminar airflow, undisturbed. But as the wind hits the mountain, the flow pattern gets disturbed and the wind flow becomes very turbulent. And there's eddies and structures start forming within the atmospheric, the air pattern. Now, if I locate an observatory here and look at Jupiter using a telescope, the light is passing through by and large undisturbed wind, undisturbed atmosphere. On the other hand, if the observatory is sitting here, the light has to pass through, coming from Jupiter, the light has to pass through this disturbed atmosphere. Now what this does is, if site A, the Jupiter will appear like this. You can see extremely fine details. On the other hand, if on site B, because the atmosphere is so disturbed, the light becomes so, the wavefronts become so distorted, and the net effect is that the fine details of the structure of Jupiter is lost. So the whole purpose of making a large telescope with a long focal length, etc., is to see fine details. Like you want to see where this eye is, these fine structures, all that is lost in this, and the ability to study Jupiter is substantially restricted if you locate your observatory here. So the observatory site choice is a very important factor in deciding how good astronomy you can do from there. Now, to put this quantitatively, if you think of the telescope as a circular aperture, which is illustrated by a coherent beam of light, as I illustrated here is a laser beam of light, and if you put a screen far away, the pattern which is formed on the screen looks like this. It's the diffraction pattern of a circular aperture illuminated by a coherent beam of light. It's not going to form one spot, it is going to form a spot with rings around it. And this is called an airy disk pattern. Now, telescope is also like this. It is just a circular aperture illuminated by, if there is no atmosphere, a plain parallel beam of light. And that beam of light at the telescope's focal plane is supposed to form an image which looks like this. So in an ideal situation, the image of a star formed by a circular aperture telescope should look like this. Now let us try to understand what is the size of that image. So if I put two stars close by, it can be shown that if with a telescope of diameter d, you will be able to resolve two objects which are as close as 1.22 lambda over d in radians in the sky. So if I use a 10-meter telescope and observe at a wavelength of 0.5 micron, the separation of objects I can see with that telescope theoretically, because of the spread of light and that airy disk pattern, is 0.01 arc seconds. So two stars are separated by 0.01 arc seconds in the sky, and I'm observing with a 10-meter telescope at a wavelength of 0.5 micron. At those pair of stars, I should be able to see them as two separate stars. That is what theoretically is predicted. Sorry. On the other hand, so I just rewrote it here. If I have a 10-meter telescope observing at sky at 0.5 micron wavelength, the central disk of that star's image at the telescope focal plane should be about 0.01 arc second. But because of the atmosphere, the image will end up being 0.5 arc seconds. So that entire light from the star, which should have concentrated on a small area like this, would spread out into an area which is 5 times this disk on the right, this green disk on the right. I can't hold a 0.5 arc second diameter disk here, is just too large. So 5 times this. So that entire light gets spread over that large area, which means any fine structure on that object which is less than 0.5 arc seconds or so will be not seen by us because it's all smudged over. They overlap with each other and you won't be able to see. So on one hand, theoretically, the telescope should be able to see 0.01 arc second size structures on that object, but the atmosphere limits it to a condition where you can't even resolve details at even 0.5 arc seconds, 50 times larger. So this is a huge limitation which the atmosphere introduces into the ability of optical telescope to see fine details in structures. Now, how do you overcome this? The overcoming is the way you overcome is by using what is called adaptive optics. I'll just quickly explain this here. I know I'm running out of time. I should finish in another 10 minutes or so. So let me rush through this a little bit. So if you have this object which you want to study in great detail, now what you need to do is to find a reference star, very bright star, very close to that, so that the light from your object, science object, as well as the reference star passes through the same atmosphere. Now this box here is the telescope with a primary mirror aperture like this. So the telescope is collecting light, and the light from the telescope, through the telescope from both the science object as well as the reference object reflects off what is called a phase corrector here. I will explain what the purpose of that is in a minute. And then it hits a beam splitter. The purpose of the beam splitter is it separates the light from the science object from the reference star. So the science object light passes through straight to the science camera. The light from the reference star reflects in the beam splitter and goes in this direction. And here there is a wavefront sensor which measures the instantaneous distortions in the wavefront introduced by the atmosphere and corrects that by changing the shape of this phase corrector. So the phase corrector's instantaneous shape is changed in a way that it exactly compensates for the wavefront distortion introduced by the atmosphere at that instant. And once this closed loop start working, the distortions, the wavefront here and here would appear as if there was no atmosphere, and you should get those iridesced pattern kind of images at the science camera with the full final fine resolution. This is called adaptive optics. I have some slides here which try to explain how adaptive optics works. I can't spend time because I'm running out of time. So I'll skip through this. All I want to illustrate here is this measurement of the atmospheric distortion and instantaneous correction is a very complex control system problem with many degrees of freedom and very little time to correct, because atmosphere is changing substantially. Substantially means it is changing enough to distort your images at the time scale of about a few milliseconds. So your closed loop system has to work faster than every few milliseconds, maybe every microsecond or every tenths of millisecond, that fast, and solve this equations simultaneously to instantaneously measure what is the distortion introduced by the atmosphere and correct for it. And this is an amazing mechanical control system problem, because the correction system, the overall control system, electronic data processing, etc., etc. So this is an amazing challenge, especially when the telescopes become larger and larger. Now, there is one limitation to this, because this whole approach crucially depends on the availability of a reference star, which is bright enough and is right next to your science target. But most of the time, if you look at the sky, there are very few bright stars available in the sky. So if you take any random galaxy in the sky, the chances of that you might find a bright star right next to it is very, very small, very slim. So while an adaptive optics system can in principle work if a bright star is available next to your target, the chances of that happening is very small. 99% of the sky, you may not find a bright enough star to work as your reference beam. How do you solve that problem? The solution of that problem is to create artificial guide stars in the sky. You shoot a laser from the telescope along the axis of the telescope, where the direction in which you are looking at, and create a beacon laser star at sufficiently high in the atmosphere, so that the light coming back from that spot of beacon, which is an artificial guide star which is created, will then measure the turbulence of the atmosphere and allow you to correct. And if your laser is powerful, you can make the artificial star as bright as you want and measure that turbulence as fast as you want and correct for it. And this is what astronomers do. So as I mentioned earlier, this is the two Keck telescopes. These telescopes have laser beacons. They look yellow because there's a sodium laser. And these lasers are shot into the sky and they form artificial stars at a certain height, 90 kilometers above the atmosphere, above the surface of the Earth. And the light coming back from those beacons are used to measure the atmospheric turbulence and compensate for it. Now, as the telescopes become larger and larger, it is not enough to have one laser beacon. The telescope will need multiple laser beacons. So I had to create a tomography of the turbulence in the atmosphere. And that tomographic decomposition of the atmosphere is now not enough to just measure the turbulence as one layer of the atmosphere. It have to measure at multiple layers of the atmosphere. And that is called the laser tomographic adaptive optics. And that is among the most challenging technological marvels which astronomy has mastered. And they will be integral part of future telescopes. So this is just an illustration of how marvelous this astronomy adaptive optics technique is. So in this thing, you can see an image toward the center of our Milky Way galaxy. We believe that there is a very massive black hole in the toward the center of the galaxy, and there are many stars which are moving in orbits around the center in tight orbits. By measuring these orbits, you can conduct various tests for general relativity and its correctness. Now, if all the stars appear really blurred out when you look toward the center of the galaxy because of the atmosphere, you can't measure their orbits. But once you turn adaptive optics on, you can see how fine those structures become. And now you can very easily measure not very easily, you can now at least hope to measure the orbits of these stars, etc. Similarly, with adaptive optics, Jupiter would, you can see how fine structures on the Jupiter you can see and how it becomes blurred without adaptive optics. This is the surface of Moon with adaptive optics. And this is the real marvel of adaptive optics. Here is a star around which there are many planets moving around. And these planets are, as you can see, pretty close to the star compared to the distance from which we are looking at it. So this angular separation from the center of the star to the planets are very, very, very tiny. Now you need to block the star to make sure that the planets become visible. And you need to have very, very highly efficient adaptive optics system called extreme adaptive optics to make sure that you have sufficient angular resolution to see these planets. And you can see 4 of them around the star. So this kind of direct imaging of planets around distant stars is really the extreme. It requires what is called extreme adaptive optics, where you really suppress the light from the central star to a large extent, to a factor of 1 billionth, for example. The star is suppressed with very little scattering so that the planets can be seen and followed. Now, the other solution is you go to space. Then the atmosphere doesn't matter. So here is a movie which shows the James Webb Space Telescope. The diameter of the telescope is 6 meters. And it's going to be launched sometime later next year in 2021, second half of 2021. So if you go to space, you don't need to worry about the atmosphere. The problem is going to space is extremely expensive. And if you have followed the story of Hubble Space Telescope, you know if something wrong goes on there, it is almost impossible to go up there and repair it. That is a very risky mission. And also, it's very, very expensive. This James Webb Space Telescope is only a 6-meter diameter telescope, and it's already cost close to $10 billion to build. It's not even launched yet. It's a close to $10 billion project. On the other hand, the 30-meter diameter telescope, which I talked about in the beginning, a ground-based facility, it is 30 meters in diameter, much bigger than James Webb Space Telescope. It cost only $3 billion to build. compared to a $10 billion program of a space telescope, which is only 6 meters in diameter. So there are pros and cons. If you go above atmosphere, you can easily get diffraction limit performance without sophisticated adaptive optics. But on the other hand, the maintaining and running that facility becomes very difficult. On the ground, you can make even bigger facilities which can be easily maintained and upgraded. But then you have to deal with atmosphere and correct for atmospheric effects using adaptive optics. Now, another solution is to go at longer wavelength, like the radio wavelength. So if you have a radio telescope, instead of collecting optical or visible radiation, you have two radio antennae, which are separated by a distance d. Then by combining the light from these radio telescopes in a precise way, you can, instead of being limited by the resolution of the corresponding to the diameter of the each dish, the resolution will now depend on the separation between these two dishes. So if these dishes can be separated by hundreds of meters, then the fine resolution you can achieve will be much, much better than that can be achieved by the diameter of the individual antenna, individual telescope. So this is another technique called interferometry. And this requires very precise time control, because the light arriving here and light arriving here would be slightly different in time. They need to be brought together and made them to combine together coherently in a way that this diffraction limited performance is achievable. Now, yes?
Sir, you have 5 more minutes.
Yeah, I will skip some of the slides and run through this. Yeah. So this is what is called a very large array, about 27 dishes, each of 25 meters in diameter, and they are separated over an area which is several kilometers across. And then there are rails on which this diameter can move around. Now, this is an even bigger technology where you have dishes separated across continents. So the baseline, this is called very large baseline array. This baseline is across continents now. You take the United States, there are antennae which are separated across the continental United States. Then in Hawaii, then there is in other parts of the world. Find the light collected by each of these telescopes in a very precise fashion, so that you can achieve the diffraction limited performance of a telescope which is as large as the separation between the antenna itself. Now, the next generation in radio telescope is what is called the square kilometer array. So just give me a moment to run this video. This is going to come up pretty soon. The construction has started. This telescope is so large that one part of the telescope is in Australia and another part of the telescope is in South Africa. So just enjoy the movie for a second. So you can see a big area full of telescopes, full of radio antennae. Huge area full of radio antennae. There's it's kilometers across, tens of kilometers across. And then there's a central part in which the antennae are packed more densely. And radio antennae need not look like dishes all the time. They can look very differently also. But this is just one patch. And that patch is in the middle of another patch, which has many more antennae. And then there are arms which are radiating out from the central patch in different directions. So if you track one of those arms, just keep an eye on the distance which is going to appear pretty soon on the video. So this is just one patch as I explained earlier. And then we are going to the next one. We are just riding through one of the arms. So this is 12 kilometers, 25 kilometers, 60 kilometers, 100 kilometers, 150 kilometers. Now we have to travel really fast. 1,000 kilometers, 2,000 kilometers, 3,000 kilometers. So a single telescope, which is 3,000 kilometers in size. That is what is called the square kilometer array. And that's going to come up. And half of that is in Australia, and another similarly large facility is going to come up in South Africa. So there are two parts of the telescope, one in South Africa and one in Australia, is enormous. So let me just quickly run through what we do at Ayuka. I clearly run out of time, so let me just quickly run through what we do. We make a lot of instruments for astronomy in Ayuka. We start with entire cycle, life cycle of design, develop, integrate, commission instruments at observatories. And I will just quickly mention 3 or 4 of these things which we are involved in. This is called a RoboAO, Robotic Adaptive Optics System. I will not get into the details of this. You can see how complicated an optomechanical system it is. And this system was developed in collaboration between Ayuka and Caltech in the USA. So you can see this is just a 1 meter size thing. And within that, how complex optomechanical system is in there. And this is an engineering marvel. Let me run through this quickly. And this is also a laser adaptive optics system, like the one I hope you can see the movie. Can you see the movie, Rinku?
No, sir. Actually, I can see the points, but there is no movie.
Okay, so then I'll skip it. So it's a robotic system which can look at hundreds of stars every night in high resolution with adaptive optics. You can see these binary stars which are well separated, which a normal telescope without adaptive optics will never be able to resolve as 2 objects. And there's an image of an AO system being built in Ayuka for an Ayuka's 2 meter telescope. And you can see the laser being shot out of the Ayuka telescope system. We skip this. The entire control system for the adaptive optics system, as I said earlier, is a very high-speed closed-loop control system which uses very powerful FPGAs, and very efficient programming is required in these FPGAs to carry out this compensate atmospheric distortions in real time. I'll skip this. And this is just a block schematic of the complex algorithm you have to build into the FPGA to execute adaptive optics. And this is a movie which shows how an introduced atmospheric distortion of the wavefront. Instead of a plain wavefront, which I explained in one of the earlier slides, the wavefront will be distorted by the atmospheric like this. And the adaptive optics system reconstruct the wavefront and correct for it. And once you correct for it, there is very little net residual. So this wavefront, if you see, is from -5 to 10, and the residuals are at the level of 0.01, 0.02. So this wavefront is very accurately measured by the adaptive optics system and instantaneously compensated for. And these systems have been built in Ayuka. We use a lot of optical fibers for astronomy. If you want to look at multiple objects in the sky and do spectroscopy, and if you want to do, let us say, collect spectrum from 2,000 objects in the sky, you have robotic systems which point your spectroscope at each of those objects and keep measuring spectra from large number of objects. This is called the Herschel Optical Telescope Integral Field Spectrograph, an instrument being built at Ayuka. This is called RoboPol. It's a robotic polarimeter which has been commissioned on a telescope in Greece about 7 years ago, and has been since then operational and been extremely successful. And like all polarization measurements, polarization being a vector, each star is divided into 4 objects here. And then from the 4 images of the star, you will then get the polarization information. We are currently building what are called the Wallops, wide area linear optical polarimeters. It's a collaboration across multiple countries, multiple institutions across the world. And we have sponsors in India of Infosys Foundation, in Europe, National Science Foundation in the US, National Research Foundation in South Africa, and so on. What we are planning to do is to build unique wide field polarimeters, 2 of them. One will go to Greece, it's called Wallop North. Another one will go to South Africa, it's called Wallop South. And these will do simultaneous polarimetric survey of large areas of the sky. Unfortunately, I don't have time about explaining what the purpose of it is. And you can see that Wallop North instrument is a very complicated optomechanical system. It has electronics, it has mechanical design, it is optical design, cryogenics, thermal control, you name it, we need it. It's a very, very engineering, really challenging instrument to design. Ayuka, we are also building what is called the Solar Ultraviolet Imaging Telescope on board Aditya L1 mission. This is the first full-scale solar mission, dedicated solar mission from ISRO. Again, large number of national and international partners. That's a SolidWorks model of the satellite, the suit payload on the Aditya L1 satellite. And we expect this to be launched sometime early next year. And it will travel to a very large distance. It's about 1.5 million kilometers away from the Earth. After, I think, the Mars mission, this will be among the farthest an ISRO payload would travel in our solar system. And this is slated to fly next year. And these things are actually designed, conceptualized, designed, developed, and built by laboratories. And Ayuka is a part of it. Finally, Ayuka is also part of this 30-meter telescope program as part of India's participation in 30-meter telescope. India's participation is led by many institutions across India, especially Indian Institute of Astrophysics in Bangalore, Aryabhatta Research Institute in Nainital, and Ayuka are the lead institutions. And as part of this, you can see the telescope structure. This is the 30-meter diameter structure of the primary mirror of the telescope, made of about 500 1.5-meter segments. And many components of these telescopes are built across the world. And just India is making a large number of components of these telescopes. So I will try to highlight what India is making. If you look at this gray thing, it is one of the segments of the 500 segments which constitute the primary mirror of the telescope. And this segment, India is making these sensors which are at the edges of the segments, which make them align with each other to 20 nanometer precision. Imagine a 30-meter surface to be made of 500 individual pieces, and each individual pieces have to be co-aligned to 20 nanometer precision in real time, while it is being disturbed by gravity, temperature, winds, all kinds of vibrations, all kinds of disturbance, even earthquakes. In spite of all that, this has to work and survive. And these edge sensors measure the tiny movements between these segments or the mirror pieces and keep them co-aligned. And these edge sensors are all being made in India. There are these actuators which receive signals from these edge sensors and make sure that the mirrors stay co-aligned. Those actuators are all being made in India. This entire complicated optomechanical support system for the segments, they are all being made in India. And out of the 500 segments, about 100 of them, actual mirror pieces also, they are also being made in India. And these mirror segments are extremely challenging to make because they are not a spherical surface, they are aspherical surfaces because this total surface is a hyperboloid. And so each mirror has a different shape as we move away from the center. And these different shapes of mirrors, as you can, there are 82 different shapes. To make them to the highest precision so that they form the part of the same hyperboloid surface is an amazing challenge. And they are all being carried out by institutes and industries in India. Let me skip through these details. So why do we do all this? Now, today, the best images you can see in optical visible light is with the Hubble Space Telescope, because Hubble is out there in space above the atmosphere. And this is a part of the sky which the Hubble will see. Hubble does see. It's called the Hubble Deep Field. Now, if we take one galaxy and zoom into that galaxy, this is the detail at which Hubble is going to see it. But if you look at the same galaxy with TMT, the 30-meter telescope, this is the detail it's going to see. You can see the real bright black hole-driven activity in the center, the arms of the galaxy, the dust lanes, the individual star-forming regions, huge amount of detail you will be able to see compared to the best you can achieve today with Hubble. So that is the major challenge of the kind of challenges which TMT is going to address. And also finally, as I said earlier, planets around distant stars, and just not detecting planets around distant stars and to monitor their orbits. With 30-meter telescope, we will be for the first time, when equipped with very powerful adaptive optic system, multi-laser adaptive optic system, we will be able to study the atmospheres of these planets and look for biomarkers, signatures of life as we know it, life biosignatures on this atmosphere, like methane, carbon dioxide. And to study that and detect those, you need telescopes which are really, and directly detect them, not indirectly, directly detect them. You need telescopes like the 30-meter telescope. So, so this is the holy grail, to detect and measure sense the presence of biomarkers around Earth-like stars in the habitable zone or Sun-like stars, Earth-like planets in the habitable zone of Sun-like stars. To detect those and measure the biomarkers in them would be an amazing challenge, which these big telescopes are going to undertake. So let me skip through this. So this is a final couple of slides. If you now take a step back and go look at what we've used to believe our universe looked like thousands of years ago. We have this in the Hindu philosophy. There is this turtle sitting on top of the Sheshnag, and there are elephants sitting on top of the turtle, then the Mandara mountain, and so on and so forth. So this is our belief, and the earth, and top of it, there are these various heavens. So this is what we believed our world universe looked like for thousands of years. Now with telescopes, things started dramatically changing. We started figuring out that the universe looked very different. At least our local universe had its sun in the center, and the galaxies and the planets going around. And Earth is just one among many planets which are going around the sun. And there are many stars in this universe which are very similar to the sun. So we are nothing special in this scheme of things. And so that whole worldview of what our universe looks like completely changed when we started looking at the celestial phenomena using telescopes. Today, what we believe is that our universe looks something like this, where we are sitting at the middle of this. This is that 4,000 megaparsec or 4 gigaparsec size of our visible universe. And as you look in different direction, it's pretty homogeneous. There is no very clear structures. It's all same in random, same distribution. And each of these tiny specks here, white specks here, is a cluster of galaxies. It's a cluster or a large cluster, big cluster of galaxies. And these clusters of galaxies arrange themselves into superclusters, and those superclusters then arrange them into these filamentary structures and so on. So we believe today that all the visible matter in this universe is distributed in this spongy structure where most of the visible matter, like galaxies, align themselves as clusters and superclusters and superclusters, which align them into filamentary structures with large empty space in between, almost nothing, huge voids in between. So this is what we believe our universe looks like with today's data. Now, the key thing is, while we see all this visible structure, like the gas and the stars, this constitutes only 4% of the total matter or the total content of the universe. We still believe that there is about 20%, 22% of the matter in the universe is dark, that it does not interact with electromagnetic radiation, and therefore we are unable to study them with conventional telescopes and conventional approaches, and we don't know what it is made of. We also think that 74% of the content of the universe is what is called dark energy, and we don't know what it is. So we have come a long way from Galilean times in understanding what our universe looks like and what it constitutes, but we still know as the best inference we have is that we know only 4% of the content of the universe. Remaining 96% is unknown to us as of today. So it's a long way to go, long way to study. Now, that is why I said this is an astonishing time to be in astronomy, to build these facilities. There is a large number of facilities which are coming up across the world, both ground and space-based, which are going to really address some of the most amazing, challenging questions you can ask about our universe. Like how and when did the universe come into existence? Can you ask anything more fundamental than that? How did galaxies take birth and evolve into what we see today, those fine structure, the large-scale structure of the universe, the filamentary structure with voids and so on? How did all that come into existence? Is there stuff we can't see, like dark matter, dark energy? What are they made of? How much is it? What is their role in the dynamics of the universe? Is there life anywhere else in this universe? If so, what kind of life? And how do massive black holes form? How do they control the lives of galaxies? And so on and so forth. So amazing questions you can ask. And these are going to produce, these facilities which are going to come up will produce enormous amount of data. So if you are a data person who would like to handle data, large amounts of data, there's an amazing challenge available. And these telescopes are going to build together simulations. Like we all probably have heard in folklore that our galaxy, Milky Way, and the Andromeda galaxy will eventually, they are moving towards each other and they will hit each other and finally form a different kind of galaxy. So these simulations, for example, is the simulation of two galaxies interacting together and the dance of the death of the galaxies. And these are going to take place over several hundreds of millions of years, or maybe even a couple of billions of years will take. This dance will continue. Eventually, they end up being, you can see in the center, a new kind of galaxy with most probably a very massive black hole. And how do you learn these things? We can't wait billions of years to learn this. They have to be simulated with existing data, with the data collected by existing telescope. They have to be simulated in accelerated time in computers. And these are massive simulations to be created. And they are also another challenge. So here is a summary of extra opportunities for engineers or others. And if you are in engineering, any branch of engineering, it doesn't matter, mechanical, civil, electronics, computer, data, any branch of engineering, astronomy has a place for you, because these facilities have become so complicated, so challenging to build that that every branch has a contribution. So for the 30-meter telescope and some of the other projects, the instruments are all being built, designed and built by engineers. They understand the engineering challenges in meeting the specification. They are all built by industries, engineers sitting in industries. Astronomers demand what performance they need to meet, but engineers are the ones who build them. If you are interested in management, for example, complex programs like the space programs, the international programs like the 30-meter telescope, the square kilometer array, multinational programs, and they really need people who understand management and even business. For example, they are run by, many of these facilities are built by non-profit corporations. So institutes across the world join together and form corporations. For example, we have a TMT, International Observatory Corporation, which is building TMT. And that corporation needs to be managed. And there is a governing board in the corporation. There is a CEO. There is an executive director. It's just like any company environment to build these facilities. And if you are a management guru, you have a role to play. Logistics, as I said, these parts are made in various parts of the world, and they have to all put together into a single telescope in one location. And shipping, logistics, management of material movement, procurement of material, legal challenges, legal rules, customs rules, income tax rules, taxation, everything is different in different countries. Environment impact assessment rules. India has just recently changed our EIA rules. So there have to be people who understand our EIA amendment impact rules to make sure that we are not violating anything while we are building these facilities. As I said, simulations, big data, machine learning, artificial intelligence, you name it, we need it in astronomy. So this is an enormous opportunity for any branch you can think of. As long as you're good at it and you're willing to put in a lot of work, we have an opportunity in astronomy. Of course, we need astronomers, finally, to look at the data and produce some results out of it. But they will come. They will come. But we need engineers first to build them, and management gurus to run the show, and legal people to make sure that we don't go to jail, and artificial intelligence people to make sure that, or big data people to make sure that petabytes of data which is produced every month, no human being, no astronomer as a human being is able to look at this data and individually study objects. They need to be done through machine learning, artificial intelligence, big data programs, and to develop those things. And astronomers will only see the end results of those, and we need for them. Now, India is actively participating in many of these facilities, like the 30-meter telescope, the square kilometer array. India is an integral part of this, and many, as you see in the case of 30-meter telescope, many of the systems are being built in India. Industries, you don't need to join an institute to work in astronomy anymore. You can be part of Larsen and Toubro or Godrej or persistent systems or ThoughtWorks and software. You can still be working for astronomy. And that's an amazing future. Thank you very much.
Thank you, sir. Now we have some questions in the chat box, sir.
So first question is from Eric Jackson.
Hello, sir. Can you hear?
I can hear you. Yes, go ahead.
Okay.
Okay, sir. First question is from Eric Jackson. What is a Magellanic Cloud? What is a Magellanic Cloud?
Yeah, Magellanic Clouds are just small galaxies, dwarf galaxies, which are orbiting around Milky Way galaxy. They are not very far. They are pretty close to our galaxy, but they are very dwarf in size. The small galaxies around which are going around our galaxy.
Okay, sir. Thank you. Next question.
You can see them in the southern sky.
Okay.
With a good pair of binoculars, you should be able to see in a good night. You should be able to see Magellanic Clouds from the southern sky.
Okay, sir. Next question is from Jamir. The question is, Suppose a star is behind a planet. How do astronomers compensate for the apparent image correction using general theory of relativity?
Yeah, the question is not very clear, but let me try to understand. I guess you're asking about the bending of light created by objects in the path of the light. A planet in front of a star is not going to change the direction of light very much because planet is not very massive and the bending is not very detectable. But on the other hand, if there is a very distant object called quasar, for example, which are very far away, extremely bright object, but they are seen very far away. And if there is a galaxy in front of the quasar along the line of sight from us to the quasar, the galaxy can bend the light in various ways and form multiple images of the quasar. And this is very often seen, and this is called a phenomenon called gravitational lensing. And this is an extremely powerful tool in studying some of these distant objects, because some quasars which cannot be otherwise studied because they're too faint becomes bright because the galaxy in front of it acts as a lens and concentrate the light from multiple directions into one point or one arc, and then you are able to study the quasar behind it. So there are instances where the bending of light is important and general relativity applies, but in the case of planet in front of a star, the effect is very minimal, unnoticeable.
Okay, sir, thank you. Next question is from Uttara Dibu. How are the orbits of the galaxy star measured? Is it also through telescope?
Orbits of the galaxies or orbits of stars?
She questioned like orbit of the galaxy star measured.
So let me try to explain for galaxies first and then maybe stars. In the case of galaxies, the galaxies themselves appear to be very stationary in sky by and large. But if you carefully observe a given galaxy over a very long period of time, you would be able to see their position changing with respect to other reference systems like the quasars, which are unmoving in the sky. So with respect to these other reference systems in the sky, like a grid of quasars across the sky relative to unmoving stars, etc., not stars, quasars, you can measure the tiny motions of the relative position of the galaxy, and from that you can understand in what direction they are moving and dynamics of the galaxy. There is also a possibility that galaxies which are part of clusters, very obviously, then you can study the motions of the galaxies within a cluster. But these are also, again, you take a long time to measure any discernible position change. Long time means tens of years, maybe several tens of years before you start seeing any discernible motion. This is one way. But if you are talking about stars within our galaxy, they are much faster moving, and especially stars which are near the solar system, their motion can be very easily observed within a given year, and within even several few months of time, their motion across the sky can be measured and their trajectories plotted with modern telescopes.
Okay, sir. Next question is from Shivapriya Prashant. How much did it cost to build the 30-meter telescope?
Cost?
Yeah.
It could be anything from $2 billion to $3 billion.
Okay, next question is from Ahmad Yassin. Why 4 images of the star? Why not 6 in that polarization slide?
Yes, it's a good question. We are only measuring linear polarization in light. We are not worried about circular polarization. So if you only want to measure linear polarization, there are 3 unknowns, which are the total intensity of light, the total light coming from the star, the fraction of light in linear polarized condition and the position angle of the linear polarization vector. So there are only three unknowns: total light, fraction of the light in polarized condition, and the position angle. So these three unknowns can be measured by 4 measurements. So if you want to measure circular polarization also, you need additional measurements. But if you are restricted yourself to linear polarization, 4 measurements are 4 simultaneous measurements are adequate.
Okay, sir. The last question is from Alf RV. Aren't ground-based X-ray telescope more effective than radio telescope?
The main problem with X-ray telescopes is that the atmosphere absorbs X-rays. So all the light which are coming in X-rays from celestial objects will all get absorbed by the atmosphere, and you will not see anything on ground. So all X-ray telescopes have to be necessarily space-based. They have to be in satellites.
Thank you, sir.
So we have come to the end of session. I hope all of you enjoyed the talk. On behalf of Rajagiri School of Engineering and Technology, I would like to thank our speaker, Professor Prakash, for giving this informative and excellent talk.
Thank you very much. Thank you for your attention. I apologize for going over time a little bit, but I enjoyed talking to you, and the questions were very good and mostly to the topic. And I would look forward to seeing many of you working for astronomy in future, because we are committed to building many of these facilities over the next 10 years or so. So unless youngsters like you come forward and work on this, we are not going to make it. For example, the 30-meter telescope, the construction may start, the on-site construction may start maybe next year, maybe in a couple of years from now, but it is going to finish construction in mid-2030s, 2033, 2034, maybe 2036. That's when the observatory is going to be ready for operation. So it's going to take more than 10 years to build it. So I'm not going to be around to use it. At least it will be very difficult for me to use it at that time. So and maintain it. So people who are young need to be part of these facilities, building these facilities, so that they become the best experts to operate the facilities and improve and upgrade them and make those wonderful discoveries. Thank you very much.